Okay, why don't we begin? So, good afternoon. Hello, everyone. Welcome to today's virtual seminar of the Qatar Centre at King's College London. For our speaker today, I'm delighted to welcome Pierre Alessandri. Pierre is currently Senior Advisor at the Banca d'Italia and also a previous colleague of mine at the Bank of England. So Pierre, a very warm welcome. Thank you for joining us. Pierre's going to speak about an incredibly important and under-researched topic, namely the macroeconomic impact of climate change. And the focus of this paper, which I think is quite novel, is going to be on not just the level of changes in temperature, but how does volatility in temperature affect the macroeconomy. So I think we have a fascinating talk ahead. For those of you who are regular kind of attendees of these seminars, Pierre will talk for around 45, 50 minutes, and then we'll have time for Q&A at the end. But if you do have a burning question as Pierre is giving the talk, then please put your question in the Q&A box at the bottom of your screens. Okay, so without further ado, let me hand the floor to Pierre. Over to you.
Thank you very much, David. Thank you very much for the invitation. I have to say I'm a great fan of the Qatar Centre's seminar series. So I'm glad we can give our little contribution to it today instead of sitting in the audience. This is joint work with Haroon Mumtaz, who's at Queen Mary University of London. And the usual disclaimer applies. So no official Bank of Italy views in this presentation. Okay, so let me start with a bit of background and motivation for what we're trying to do here. I think we all know by now that climate change has at least two important dimensions. The first one is global warming, rising temperatures and precipitations that have increased globally in most regions of the world in the post-war period. There's a second dimension, which is an increase in the variability or volatility of temperatures and precipitations. What you see here on this slide are a couple of quotes from the report published by the Intergovernmental Panel on Climate Change in August 2021. And quite a lot of the report discusses volatility type of issues. So they say that the frequency and intensity of heavy precipitation events has gone up a lot since the 1950s. A similar increase in droughts was also observed, and hot extremes have become more frequent and more intense. All of which speaks to a rise in the overall volatility of the climate system. I also added a nice chart from an FT article that came out only a few weeks ago in mid-January. And basically what the FT is showing here is the number of adverse weather events and disasters in the US since the 1980s, and an estimate of the associated economic costs. I think this chart and the article are interesting for a number of reasons. So first of all, the number of unusual events rose steadily since 1980. And you can see that from the grayish bars in the background here. Secondly, the impact of those events, which is a proxy also of the actual severity of the events, became a lot more volatile. So broadly speaking, there is a long phase, 1980 to early 2000s, where, you could get away with losses in a range of $0 to $2 billion. And then you move to a world where this range is rather like $0 to $20 billion, which is, quite a different situation. You don't see it in the chart, but the article is nice also because it notes that 2021 was also marked by a really strange mix of wildfires, winter storms, and hurricanes. So, these are, if you like, three different ways of interpreting or three different dimensions of this increase in volatility. Now, what's interesting about this is that we know quite a lot about the level effects of climate change and not much about the volatility effects. What do we know about levels? Well, this has been the subject of a pretty long a pretty long research effort by now. In short, we know that rising temperatures are generally bad. They have a negative effect on economic activity. We have more recent papers that came out in the last 8 or 9 years that focus specifically on weather anomalies or outright disasters, for which causality can be established in a much more convincing way, I guess. And they show that these are also really bad for growth. And then there is a long debate on the distributional or cross-sectional implications of these shocks, which basically points to this key fact that your level of development and income is a good proxy of your vulnerability towards climate shocks. So poor and agricultural countries are more vulnerable. We do not know much, by contrast, about volatility effects. And the specific question we want to address in this paper is whether, to what extent, household and firm decisions depend on their perceived level of climate uncertainty. Now, why should this matter at all? We believe there are at least 2 mechanisms that could that come into play here. First and foremost, a volatile climate could cause income volatility to become higher. That's kind of obvious, or maybe mechanic, in the sense that if you have in mind a model of this nexus between climate and economy, where temperature, in which for some reason temperatures affect GDP, then it's very likely that volatility in temperatures is going to cause volatility in GDP. You don't even need to be specific as to how this link works. But if the levels are connected, then the second moments are likely to be connected too. And then there is a second mechanism which operates through the growth level. We know from the macrofinance literature that there are various situations in which an increase in risk or the volatility of some economic fundamental is going to have a negative effect, first-order effect on GDP dynamics, because people consume less, they start investing less, and so on. And it's entirely likely that climate volatility may trigger a similar response. To answer these questions, we basically propose in this paper a new panel VAR model that we can use for 2 purposes. The first one is to measure the conditional volatility of climate across countries and over time, which is a task in itself, I guess. And the second one is, through appropriate restrictions and some sort of identification, to say something on causality, and by which I mean estimating the impact of a change in the volatility of the climate system on GDP growth. Okay, so this is a one slide summary of the paper. We have a panel VAR. We have a data set with 133 countries that runs for the 1960 to 2019 period. The model that we propose, as you will see in a second, has 3 defining features. The first one is that it's a VAR. So we are thinking of a setup where temperatures and GDP interact endogenously. This is important because in many traditional panel regressions on this climate and growth literature, you have GDP on the left, temperatures or precipitations on the right, and there is a presumption that there is a strong exogeneity of these covariates with respect to economic activity. We don't want to have that, so there is an endogenous interaction between the two. The second key feature is that we are going to let the conditional volatilities of this series change over time. So it's a heteroscedastic model where the residuals can have a high or a low volatility. And finally, there is a volatility mean mechanism. So we want to have a regression, an empirical framework where a change in volatilities can have an impact on the dynamics of the level of the variables. What do we get out of this? Well, in terms of measurement, the model suggests that the volatility of annual temperatures, call it sigma T for now, went up almost everywhere in the last 60 years. To give you an idea of the magnitudes, we end up estimating increases in sigma t of 0.1 to 0.4 Celsius degrees. And then the impulse response analysis reveals that volatility matters for growth. And the two mechanisms that I was sketching on the previous slide are both active and quantitatively interesting. In particular, it looks like a 1 degree increase in this annual temperature volatility can cost you a 0.3% drop in GDP and a 0.7 increase in the volatility of GDP. Another interesting result is that although there are differences between rich and poor countries, these mechanisms seem to play out roughly in the same way for all the economies in our sample. So if you had to sort of step away from the specific results we get, I guess the two broad implications of our analysis are that, first of all, you can't really think about climate change in terms of levels only. There are significant costs to climate change that might be coming from this change in the second moments of the data. And another interesting implication is that climate risk might actually affect us now, ex ante, not just ex post. So uncertainty of what the world will look like in 20 years might be, influencing consumption or investment choices already. Okay. I want to say something on the literature, then I'll talk about the model and the data. I'll show you the main results. And then I have a bunch of additional results in terms of robustness or the nature of the transmission mechanisms that we may or may not get into depending on how we're doing with time. Okay, so broadly speaking, we see this paper as sitting at the intersection of two types of research. The first one is, or two themes, if you like. The first one is climate and growth, on the implications of climate change for economic activity. This was traditionally studied with integrated assessment models. Then there was an effort at modeling this stuff in general equilibrium. There's a really long list of works that tackle this question using cross-sectional or panel data sets. And then, as I said, there's a more recent research that looks specifically at the role of weather anomalies and disasters, including a paper by Kim, Mattes, and someone else that was presented in this seminar series not long ago. And basically, the key message from these guys is that, rising temperatures, weather anomalies, and extreme events are all recessionary to some extent. They all have a negative impact on GDP growth. The second line of research has to do with the role of risk and uncertainty in the economy. I didn't even try to summarize the key references here. Obviously, we do it in the paper, but basically these are some of the big names who contributed to this literature: Bloom, Cristiano, Fernandez Villaverde, and so on. And there is a nice survey paper by Jesus Fernandez Villaverde that gives a good summary of what has been said and done on this in the past. What comes out of this bunch of papers is that macro financial volatility, so volatility in economic fundamentals, can have a first-order effect on income and growth. So basically, the question we ask is simply, if you like, whether climate volatility is also a potential driver of the business cycle, and whether the climate system can be a source of the volatility shocks that these people have studied before in different contexts. I have to say a few words on three papers that are clearly more closely related to what we're doing: Donatelli et al., Kotz et al., this is a Nature paper, and Linsenmayer, 2021. So in these cases, you have studies of the relation between the realized variability of temperatures and growth or development. And we believe we're doing something, conceptually different here. The reason is simple. if you regress output on realized volatility, you're basically regressing output growth on a function of the changes in temperatures that you observed in the recent past, right? And it is easy to show that basically volatility is, heavily dependent on the size of the shocks that you observed in the past, which means that if the link between temperatures and GDP is nonlinear, volatility may end up correlating negatively to future GDP simply because it's capturing the impact of large level shocks. I don't want to get into the detail, but there is a paper, a Ristad paper by Berger, Becker, and Giglio, where realized volatility is used as a control to identify uncertainty shocks. So what they say is, if you want to have a chance to isolate an uncertainty channel, you have to control for the impact of big shocks. So there are two conceptually different mechanisms. What we want to isolate is the role of risk and uncertainty. And the questions we have in mind is, whether people realized that temperatures were becoming more volatile, and how, if at all, they responded to this increase in or decrease in predictability. And basically, our model is designed in such a way to give us an ex ante measure of volatility that does not correlate with past shocks, and that in theory should capture expectations on the future volatility of the state variable that you're interested in. I'll just show you the results of a simple simulation to convince you that this is an interesting mechanism to look at, and then maybe I can stop for questions for a second. Now, is the risk uncertainty story plausible? We thought that a good way to answer this question was to turn to an established general equilibrium model of uncertainty, the Basu-Bundik Econometrica 2018, and just try to force a climate block into the model. So this is how we did it. We assume that there is an exogenous temperature process with a stochastic volatility component. And then we kind of postulated that temperatures had a negative impact either on productivity or on the discount rate that households use to evaluate future consumption streams. On top of that, to be even more agnostic, we considered two cases. A linear one, which basically assumes that higher temperatures are bad for productivity, and the quadratic one, in which case the assumption is that there is an optimal temperature level around which the economy is, at its maximum efficiency, and that fluctuations around this level T are bad for whatever reasons. And we found that, using a pretty conservative calibration of these gamma parameters, we found really strong evidence that uncertainty can be important in this context. So what you see here is the impact on output, consumption, and investment of 4 specifications of these models. So we are letting temperatures hit productivity or discount factor under a linear or a quadratic specification. As you can see, the dynamics change in interesting ways. So investment doesn't always go down, for instance, whereas consumption does. But the upshot is that these mechanisms are all, in principle, capable of generating a non-negligible contraction in output. So we believe the story conceptually makes sense, and the question is whether you see it in the data or not. David, unless there are questions, I'll just move on with model and data.
I don't see any in the Q&A, but I do have one quick one myself, so I'll ask you at this stage. And it is, you've touched on it already with this previous slide, but I was wondering if you could say a little bit about, I guess, the connection between the VAR you're going to estimate and these kind of more theory-based integrated assessment models, or the Alessandri model you mentioned. I realize they might be more of a deterministic sort of thing, but can you think of your VAR as like the empirical counterpart of those models, or there are some interesting differences? That would help me a little bit if you could touch on that.
Yeah, no, I think, no, you're right. So I would have to think a bit about the connection with the Acemoglu paper. But the way I see it is precisely as a rough, empirical, reduced form approximation to what these models are trying to capture. The only difference is that we obviously have no explicit characterization of this linkage between economics and climate. In the baseline version of the model that you will see in a second, we simply have a VAR with GDP and temperatures. We add this stochastic component that is missing, especially in the integrated assessment models, but we are not going to say anything on, we are not going to say much on the mechanisms through which these shocks propagate. We do have a bunch of results on how investment, consumption, and sectoral output moves in response to this shock. But it's quite a long way from the full picture of the transmission mechanism that a DSG model can give you. But we need to think about it. I mean, there might be ways of testing specific implications of, say, Acemoglu or Golosov using our framework. So it's a good point.
Thank you.
Thanks. Okay, model. This is what the model looks like. Suppose you have a vector of variables, ZIT. The variables are indexed over countries I and years T. In the baseline specification, I just said it, I guess, I'm going to repeat it. We will look at a small system where Z simply consists of the average annual temperatures in country I at time T and the annual GDP growth rate in I between T and T-1. So this is like our minimalistic setup. And we are going to model it this way. So there will be some country-specific fixed effects, potentially some time fixed effects, and then lags of the ZT variables. So if you ignore for 2 slides this mysterious H tilde term up here, what you have is an ordinary panel VAR model. The only useful thing to keep in mind, if you are used to seeing panel regressions or cross-sectional regressions, is this idea that here you have two-way interactions. So temperatures are not exogenous to economic activity as in standard panel regressions. And obviously, in this regression, the residual term by construction captures unexpected annual changes in temperatures and GDP. Now, what do we do with these residuals? In a standard panel VAR, you would basically think of the covariance residual matrix as a fixed object that just tells you how correlated these surprises in temperatures and GDP are on average in your sample. And what we're going to do here is to turn it into a time-varying object. So it's a matrix that is driven over time by changes in these log volatilities HT. So each variable has its own conditional volatility series. And the volatilities follow a panel VAR1 process too, with their own volatility shocks. What are the implications of this setup? Well, we are basically assuming that the volatilities of the residuals of T and GDP are affected by second moment shocks that leave the levels unchanged. So there is stuff that can happen in a given country at a given point in time that widens the distribution of the residuals without actually changing the observed temperature level. And through this panel process, we're also allowing for interactions between the volatilities of T and GDP. Now I'm pulling together equations 1, 2, and 3 to give you a bit more sort of comments on the nature of the model and say something about identification. So once you pull everything together, you have your endogenous variables, you have residuals that have a time-varying volatility structure, and you're sticking your estimated volatility back into the model as an additional regressor, okay? So basically, this is a setup where volatilities change over time, and through these gamma parameters, in principle, a change in volatility can have implications for the dynamics of the levels of the variables. So whether volatility matters or not, to quote Jesus, boils down to an empirical question on the significance and magnitude of these gamma coefficients. Now, the model has 2 level shocks and 2 volatility shocks. It's 4 shocks in total. Everything is endogenous. So as usual, as in a standard VAR setup, you need identification restrictions to attach some kind of economic interpretation to the shocks. And we use 2 assumptions. The first one is that eta and V, volatility and level shocks, are orthogonal. So there are no factors that systematically affect both first and second moments. And the second one is Cholesky. We assume that this H and A, B0 and A matrices are lower triangular. In practice, that means that GDP does not affect T within a year, either in level terms or in volatility terms. Okay, so this is Cholesky. No one uses Cholesky in the empirical macro literature anymore for very good reasons, because in many setups, this assumption of having a recursive structure in the economy makes no sense. But we believe that in this context, it actually works, because although it is certainly possible that temperature respond to development and growth over a medium to long-term horizon, nobody really expects this feedback to work within a time period, meaning a year in our case. So this is a weak exogeneity of the climate system to the economy, which is, in our view, quite defensible. One slide on the estimation. This is my co-author's work, so all I can do is to try and summarize it without getting it all wrong. This is a Bayesian model, so we estimate it through a Gibbs sampling algorithm. And basically, the algorithm that Haroon worked on is an extension to a panel setting of a technique that is actually, widely used for ordinary Bayesian VARs with stochastic volatility. I won't even go through this list. Basically, because it's a Gibbs sampling algorithm, obviously the key is to partition the parameter space into blocks that have a known distribution that you can sample from, holding everything else constant. And this sequencing does the trick. As I mentioned earlier, we have an unobserved state variable, actually 2 unobserved state variables, which are these conditional volatilities of our series that get sampled and drawn stochastically, conditioning on the parameters. So we estimate parameters and volatilities at the same time, jointly. And there are various numerical criteria that you can use to make sure that this estimation process converges, is well behaved, and so on. There's a really long annex in the paper that goes through the technicalities of this estimation problem that is not completely standard. A few words on the data, and then I think we'll move to the results. In terms of macro series, we get everything from the World Development Indicators database of the World Bank. Most of the charts you will see in the next 20 minutes are based on real per capita GDP. We then have a section on the transmission mechanisms, where we try to look at investment, consumption, and value added in various sectors, using slightly more granular economic indicators. Obviously, the key ingredient of this analysis is the climate data. And here we opted to use 2 alternative data sets. Our baseline estimates are basically based on the data set used by Dell et al. In a widely cited AJ Macro paper on temperatures and growth. The reason why we started from here is that these numbers are really well known in the literature, and that the paper gives us a really good benchmark to evaluate the plausibility and economic meaningfulness of our results. An interesting detail of this fact about this data set is that the country level aggregation, obviously temperatures and precipitations are sampled at the station level, and what the authors do in this paper is to produce country level aggregates using population weights that are fixed at the end of 1990. As an alternative, we resort to a data set assembled by the University of East Anglia Climatic Research Unit. The data set is public, you find it here, and it's live. So our sample ends in 2019 in this case, but it's, I think it's been updated last year. It's technically more advanced. There is a detailed background documentation that explains why this measurement is better than many alternatives. There's a question mark here because I personally didn't quite understand what the difference is, but I have no expertise on this, so I'm happy to take the claim at face value. One difference that I do know how to interpret is that the country level aggregation here is based on area rather than population weights. So, we're also validating our results along this dimension. Okay, let's move to the meat.
Yeah, before you get into the meat, can I just pass on two questions that have popped up at this stage?
Yeah.
So one concerns the model specification. So Sushil Matthew asks whether there's a literature that suggests that you think the level and volatility of temperature might have a multiplicative effect rather than just an additive effect. If you could comment on that. And the second question, you might want to kind of take this in the round as you're doing the results, but our former colleague Lavan Mahadeva asks how the volatility shock estimates you're about to show us, how do they compare to the level effects from the previous literature? But take that how you like.
Okay, so Lavan, hello, thank you very much. I will show you a couple of charts where you see this comparison directly. So I'll postpone. Feel free to ask again if you're not satisfied, but I'll postpone your question by 5 minutes, I guess. Okay, yes, multiplicative effects. I would have to think about it. So these are log volatilities, which might to some extent help us catch the nonlinearity you have in mind. If instead what you're thinking of is an interaction between levels and volatilities, I think that our modeling setup can handle that, but we haven't looked into it. So to be clear, in this setup, a volatility shock is going to be orthogonal to levels. It will have no impact on no mechanical impact on the level of temperatures. And yes, as you can see from here, it's linearly related to GDP. So I'll take note that there might be more interesting or even less linear ways of setting up this conditional mean equation. I have to say I don't know the literature on the. I can't think of any papers where they look at these multiplicative effects. So if you have references and you can share them with us, that would be useful. Okay, thanks. Okay, results. Trends in temperature volatilities. So what does the model say on how the conditional volatilities of annual temperatures moved in the last 50 years or so? Okay, what you see in the left panel of this chart is the total change in temperature levels for 6 large geographical regions. This is just the data. All we did was to adapt or take averages. All regions, by the way, are simple unweighted averages of the countries that belong to them. So you have Middle Eastern North Africa, Sub-Saharan Africa, and so on. And the left panel simply shows what global warming means in the DJO data set. You know, temperatures went up by something like 0.5 degree Celsius to 1 degree Celsius across the board. The right panel is an output of our model, and it shows you the average increase in the conditional volatility of annual temperatures in these 6 regions. And we think it's a pretty striking picture, because basically the trend you see in the level is, you know, also pretty clear. In fact, in many ways clearer when you look at temperature volatilities. Another interesting thing is that the regions do not really behave in the same way in these 2 panels. Let me point you to a specific example. Sub-Saharan Africa, my screen is bad. I think it's a dark orange band. Experienced a pretty large increase in temperature levels over this period, but saw little or no change in volatility. Whereas Western Europe and North America, purple, had exactly the opposite experience, right? Nothing much happened in terms of temperature levels, but the volatility of annual temperatures increased quite a lot. So you can get a sense, even at this level of aggregation, that there are dynamics that differ between levels and volatilities. And now this might be useful, I guess, in response to Lavan's question. We are now moving down one level of aggregation, so we have country level data. And what I'm showing here is the cumulative change in temperatures over the entire sample period and the cumulative change in temperature volatility on the y-axis. The size of the bubble is a country's average GDP level in the pre-sample period, in the 1950s, which are not part of our estimation sample. And this is a cool chart. I mean, it's useful and promising from an identification perspective, because basically there is no correlation between these 2 objects. It's just, you know, a cloud of random points, or so it looks. And there's another interesting feature coming out of this, which is that if you look at temperature levels, you can see that, you know, the large increases are mostly attached to small or poor, relatively poor countries. And there is a bunch of wealthy developed economies that basically experience no change in temperature or even a negative change in temperatures. Whereas if you slice the chart horizontally, you can immediately see that when it comes to volatility, there is no big difference between small and big. So most rich economies in our sample saw an increase in temperature volatility of 0.1 to 0.4 Celsius degrees. So they're pretty uncorrelated. It's promising from an identification perspective, because obviously if you had a straight line and, you know, levels and volatilities moved in tandem, then you would have really slim chances of identifying a separate uncertainty channel. I'm going to skip this and move to the impulse responses, I guess. So here I made a choice for this presentation. Because it's a VAR, you can obviously look at this n by n plots of responses of everything to every single shock in the model. We are not going to do that. So the model generates a lot of results that are really not surprising in any way. Level shocks have a persistent impact on, you know, their target variables. We find that an increase in temperature levels has a negative impact on GDP, but only in poor countries, which is totally expected on the basis of what we know from the literature. We also find that shocks to the volatility of the GDP process have mildly recessionary implications, which again is not a surprise. So what I would like to focus on in the next 4 slides is the shock that we are writing the paper about, which is a shock to the volatility of the temperature series. What happens if temperatures become more volatile for exogenous reasons, where exogenous has to be interpreted in the VAR context, of course. Well, first, you see a drop in GDP growth of roughly 0.3 percentage points that persists for about 4 years. And secondly, you see an increase in the conditional volatility of the GDP process of 0.75 percentage points that instead has virtually no persistence. So basically, an increase in climate volatility gives you a fairly long contraction in economic activity and a contemporaneous increase in the volatility of the GDP process. So this means this is a within year effect. It means that volatility, GDP becomes more erratic in the year for which you observe higher temperature volatility. And obviously, I'm showing these two charts together because if you were to think about these mechanisms from a welfare perspective, you would presumably care about both, right? So the shock gives you a lower consumption level for a while, and it also complicates your life if you want to do consumption smoothing because you don't really know how much, what level of income you will get at the end of the year. Let me give you a flavor of what we thought about in terms of robustness analysis so far. I think this is an unfinished business, obviously, so I mean, ideas would be welcome. Chapter 1, heterogeneity and stability. We do the usual sample splits between poor and rich countries, hot and cold countries, share of agriculture, to see how heterogeneity works for the shock we are studying. And then we do just a simple sample split in 1980 to check the stability of the estimates over time. Chapter 2 has to do with confounding factors, and particularly with the impact, with the potential influence of big level shocks to T or GDP. So what we do is to estimate a larger model with precipitations. Then we add the square change, the square GDP growth, which hopefully is going to capture the impact of recessions and crises in this panel. Then we add a rough proxy of the realized volatility of T. So, we agree that big shocks might play a role. So we want to make sure that our uncertainty shock is identified cleanly, controlling for this stuff. For the same reason, we also add squared volatility terms. And then we do more of a, if you like, a panel type of control, which consists of adding year by region fixed effects. So these are not fixed. I mean, they're called fixed effects, but they vary across regions and over time. And finally, as I mentioned, we just throw away the data set, the climate bit of the data set, and we replace it with the CRUTS data. I have background charts on this, but I thought I could simply show you maybe one table. This is the contemporaneous impact of the shock across specifications on GDP and GDP volatility. So the central column here gives you an idea of the stability of the point estimate at the median. As you can see, it doesn't move around very much. It's actually even larger in the CRUTS dataset. It goes from 0.3 to about 0.4%. And the same is true for the volatility, for the impact on GDP volatility. The significance of these estimates bounces around a little bit, but in most cases, when you look at the long-term impact of the shock at the five-year horizon, you see negatives, a significantly negative impact in all specifications. So none of these tests raises doubts in our view on the existence of the mechanism. Okay, I think I have a choice between showing you one of these charts and saying something on the transmission mechanisms. So I'll go for the second option. Okay, this is even more work in progress than the rest of the paper, but basically what we try to do is to come up with a sort of clearer view of which transmission mechanisms are activated by these changes in volatility. We believe this is a really tough question to answer, because basically there is no agreed answer for level shocks either. This GEL survey by Dell et al. Basically lists and documents a really long list of economic fundamentals that are affected by changes in temperature levels: consumption, productivity, trade, migrations, health, mortality at some, reasonably long horizon, of course. And although macroeconomists are kind of debating whether these shocks can be framed or interpreted as supply or demand shocks, we believe that, we haven't got there yet. These are shocks that can change at the same time productivity and cause wealth effects, or change the discounting of households and entrepreneurs. So basically, it's really hard to see them as demand side or supply side shocks. And there's another complication, which is that the propagation changes a lot across countries. So Parker finds that natural disasters, including climatic shocks, tend to raise inflation in rich countries and tend to reduce inflation in rich countries and increase prices in emerging countries. So, it's really hard to pin down a single transmission mechanism in a large panel. Anyways, we do try to say something about this. And to do it, we basically estimate alternative specifications where we replace GDP growth with investment or consumption, and with the share of value added over GDP in the manufacturing, services, or agricultural sectors. And this is what we get. So investment and consumption both fall in response to an increase in volatility. You also see a large drop in the value added for manufacturing and services. Interestingly, you don't see that for agriculture at all. In fact, we estimate a marginally significant increase in value added for this sector. It would be tempting to interpret it, to look for a structural interpretation of this. So there are people who find that food prices jump a lot in developing economies in particular when you have volatile temperatures. So, this might reflect a relative increase in the inflation of, the final goods of the agricultural sector, or it might be something else. We are not in a position to really attach a specific interpretation to this. One interesting thing is that this also acts as a robustness check, if you like. So we are also making sure that the GDP drop we see in the baseline estimates is actually consistent with the behavior of the main components of GDP. But these are average results based on 133 countries and 60 years of data. So again, we can't credibly identify a specific unique transmission mechanism. Okay, I think I'm more or less on time. And I can see some action in the chat. So let me conclude. The premise of this work is that we know that climate conditions and weather shocks influence economic outcomes. We notice that most of the literature focuses on the implications of, I'm saying changes in temperature levels. What I mean is level shocks. So changes in temperatures and precipitations, or the specific role of disasters and extreme weather events. Our contribution to this literature is to investigate the volatility or uncertainty mechanism. And the question is whether volatility matters as it does in other realms. So we propose a panel VAR model that is capable of capturing the endogenous interaction between temperatures and GDP, and does give a causal role to temperature volatility shocks. So we can estimate the conditional volatility identify with some restriction exogenous changes in volatility and trace the impact of those shocks to GDP or other economic indicators. And our estimates, based on this large panel, basically deliver three key messages. So first of all, volatility went up almost everywhere. So in a way, the model backs up the layman's view that weather and climate conditions are all over the place and they're not as predictable as they used to be. More importantly, it provides really statistically convincing evidence that higher volatility leads to a lower and more volatile GDP pattern across countries. And it also shows that, rich developed economies are not quite as immune from, as isolated from climate shocks as maybe they think they are. Which means, on the one hand, that the real costs of climate change may be higher than we think, and on the other hand, that there is an uncertainty effect that is playing out right now. So you don't need to wait for a disaster to happen to pay or feel the cost of climate uncertainty. All right, I think that's all I have, David. Thanks.
Fantastic, really interesting, and bang on time as well. So I see Haroon has also joined, who can help you answer the questions that we get. So there's a few in the Q&A which I'm going to relay to you. If anyone else has questions, please do type them in the Q&A box. Let me start with a question from Raghav Mathur, who asks, there's a question about the robustness of the results to kind of focusing on countries that are more susceptible to temperature changes, countries that have experienced climate disasters, countries around the equator, for instance. So if you could speak about that a little bit. And then a second one, why don't you take at the same time, by my colleague Tim Foreman asks, can you remind us what the typical value for volatility, I think, of temperature is, and how much it's increased in the past 50 years, to get a sense of the magnitude of the effects you're actually estimating? Why don't you take those two first?
Yeah, absolutely. Right. Okay, so yes, heterogeneity and the potential difference between, let's say, safe countries and not so safe countries. This is really interesting. We haven't done it. I would guess, well, it's not obvious, but yeah, I mean, an easy guess is that countries that experience or often experience disasters are somehow more resilient to the uncertainty effect, either because of psychological, behavioral factors. You're living in a world where you've given up on predicting climate conditions anyway. So it doesn't really matter whether the volatility goes up or not, or because you have in place insurance mechanisms that work better. Not sure that's the case for poor countries, but yeah, no, it's a very good point. We haven't done it, and we will look into it. The second question was on the scale of the effect. Let me try to go back. What else can I say on top of this? Yes, I see where you're coming from. So the 1 Celsius degree shock that we are using in the impulse response analysis is a big shock. I don't remember off the top of my head what's the estimated standard deviation of the shock, which is what you will need to scale it properly. But as you can see, we are talking about a cumulative increase of 0.2 or 0.3 percentage points for this series. So this is not a typical annual shock to temperature volatility. It's a big one. To be more specific, I would need to check the numbers. But yes, thanks for asking. It's an important point.
Great. Okay. Let me pass on a few more. So this one is in the chat from Joshua Ostry, who asks, whether these kind of volatility shocks, do they transmit themselves into a larger variance of GDP growth, or is it in addition a larger left tail of the growth distribution? You want to take that?
Good point. Thanks. Well, in our model, they translate into a larger variance because everything is symmetric, right? So we are basically modeling just the first and the second moment of this distribution. It might be possible to say something more specific on the left tail, but you would need a model where you have a left tail. We don't have one. We just have a log volatility that changes over time. To be honest, I don't think. So I think the symmetry of the temperature distribution is a reasonable assumption in the sense that the IPCC report shows that basically you have, a widening of the tails in both directions. This is like the, heavy rainfalls versus droughts issues. It would be interesting to see if there is an Adrian Boryachenko-Giannone type of effect, and you thicken the left tail of the GDP distribution. We cannot do it in this context, but maybe we can think of a way to do it off model. Thanks.
Perfect. My colleague Reese Bidder has a question as well. Reese, do you want to ask directly?
Yeah, sure. I was just wondering sort of what you might do out of model to sort of test these things, whether or not some sort of local projections or something like this, or maybe if there's data on the term structure of uncertainty that you can, because your model, you can crank your estimated VAR and get very strong predictions for these objects. And it'd be good to see sort of a sanity check from some other part of because I'm just very aware that we're bad at modeling dynamics at the best of times in macro, let alone things that may be tipping points and where our impulse responses maybe don't actually respond for a long time, and then 50 years later pick up. So this whole AR1 and the necessity of a shock today to get the predicted volatility in the future to rise is maybe an artifact from our macro ideas, whereas maybe the whole dynamics are not quite suited to the VARs. But it's a heroic, very interesting paper as well. It's been sort of fascinating.
Thanks, Rhys. No, you're right. I have to say, I think Haroon is, not well, to put it mildly, not enthusiastic about using this two-step approach. Using a model to estimate the shocks and then the local projections to, see what happens to X and Y, for good reasons. But you're right. So we can try to think of a way of, eluding the straitjacket of the panel VAR and sort of validate our shocks against some sort of third independent, an independent bunch of variables.
And I guess maybe just to follow that, maybe a simplistic question is that when people say, well, this is the effect, the long run effect of GDP growth or whatever, do you have some stationarity in your model that's already preventing you from saying, okay, we're going to have a long run integrated effect of what we're doing now on the level? I wasn't sure if you were imposing that everything reverts back to mean eventually in this, or whether you accounted for that.
We are, in the sense that we're modeling GDP growth rates. So we already throw out of the model most of the trends that maybe you're thinking about. So if these shocks have a long-lasting effect on productivity that really change your potential output, then we are basically looking at half of the story. You should set up a model with the trends and see what happens there. But yeah, no, it's I think it's an interesting avenue for. It's on one side, it's about understanding better what the implications are. On the other side, it might be useful to, as you said, validate the analysis and convince readers that the shock is identified in a reasonable manner. We can speak about this later. Actually, I'm interested in collecting ideas on what we can do on this front.
Yeah, let me pass on. If you have a couple more minutes, so a question from my colleague Franz Burkouts, who thanks you for a great presentation to start with.
Thank you.
And then one question is your definition of temperature volatility. Is it the mean temperature over a year for a whole country? Or are you using a measure of temperature which is more temporally or spatially detailed? I must say I have a similar question in my mind when you were going through this. This is in relation to critical events like heat waves.
Yes, very good question. So, so where did I want to go? Well, it doesn't really matter. So the answer is option one. So keep in mind how this thing is calculated. So all we put into the model is a single series of average annual temperatures for country I. Okay, so what we're extracting is the volatility of the residual of this series. So it's basically aggregated at the country level, and it doesn't. It only indirectly captures the within year volatility. I mean, this is good and bad. It is, high frequency data give you a lot more traction on this phenomena. There are seasonal patterns. There are even within months patterns. But if you think about the ex ante impact of uncertainty, we think it's a good approximation. So if you were to plan an investment in vineyards in California, you're not really worried not just worried about, daily spikes, but you really want to have an idea of what the climate conditions on average will be for the next 10 seasons. But yes, it's at the country level and it's annual. So there is no granularity in that sense.
Thanks for clarifying. And Friends also passes on a reference in Nature, which I'll send you separately. I'll send all of these questions over to you.
Yep.
Okay, I think let's draw this to a close as we're past the hour. So let me just thank you, Pierre and Haroon in the background, for really a fascinating talk today on a really important question. I've certainly learned a lot. So thanks for your time, and thanks to everyone in the audience for your questions. We'll see you in a couple of weeks.
Thank you very much, David. Thanks, everyone.